In the previous videos, we've been talking about the metric system and units and how important it is to have the appropriate units for particular measurements. One of the things we need to be able to do is to convert one unit into another. That would have helped in a lot of those mishaps we talked about previously, the Mars lander and the jetliner in Canada. If only people had converted the units correctly, those disasters could have been avoided. So let's take an example here. Suppose I wanted to know how many feet there were in 2 yards. If I asked you that question, I don't think you'd have a lot of trouble answering it. You would probably simply take the 2 yards and multiply it by 3. And if you did that, you would probably tell me that the distance was 6 feet. But that's not actually the answer we get. If you take 2 yards times 3, you don't get 6 feet. Instead, you get 6 yards. We can't simply just throw away the unit of yards and replace it with feet. Think about how you do algebra problems. If I gave you the problem in math to multiply 2z times 3, would you get 6y? Of course not. You would get 6z. That z cannot simply be dropped. Nothing canceled it out, and so it's going to remain 6z. What we really need to do is use something called a conversion. And a conversion is basically a fraction that relates 2 different units. In the case of feet and yards, that conversion is 3 feet equals 1 yard, and that of course is where you got this 3 from in the first place. Now if we multiply 2 yards times 3 feet per yard, the first thing you notice is that the units of yards cancel out, and we end up with feet as our unit, and this time we will indeed get 6 feet as our correct answer. So when you're using conversion factors, there are 3 things that are important to recognize a conversion factor. First of all, they're always fractions, like the 3 feet per yard. Second, they have to contain 2 different units. It's normally the unit you're starting with and the unit you would like to get to. And then finally, they have to equal 1. Anytime you multiply a value by something, you can't change what its value is. If something is 2 yards long, you can't suddenly make it 6 yards long. So the only thing you can really multiply a value by is 1, and there's a lot of ways to write the number 1. For example, 16 ounces per pound. That's a conversion, and it's equal to 1 because 16 ounces is the same as 1 pound. 4 quarts is equal to 1 gallon, so that conversion is equal to 1. There are 5,280 feet in a mile, equal to 1. 100 cents in a dollar, same thing. And 24 hours in a day. All 5 of those conversions, they're all fractions, they all have 2 different units in them, and they all equal 1. All right, let's go ahead and try a few practice problems just to make sure you're getting the hang of this. So we'll start out fairly simple. How many ounces are there in a pound? Well, we'll start out, of course, with whatever our given value is, which is our 3.75 pounds. We always want to begin a conversion problem with a known value, and we try to find the unknown, which in this case is ounces. Now, to get from pounds to ounces, we need a conversion that relates those 2 units, and we have one, which is 16 ounces per pound. Again, you can notice that the pounds cancel out very nicely, and we end up with an answer of 60 ounces. Now, you're probably thinking in some of these problems where there's only one step, this seems like an awful lot of trouble. But the problems are going to get more complicated. We're going to have problems with 4, 5, or even 6 steps in them. And in that case, you're going to find it very useful to set these up the way we're doing it. Okay, how many minutes would equal 3,740 seconds? Our starting point, of course, would be the seconds. We need a conversion that relates minutes and seconds, and of course we all know that there's 60 seconds in 1 minute. Now, an important thing for you guys to recognize here is you're probably used to writing conversions where the number is on the top. You don't normally write it 1 pound over 16 ounces. But the fact is, all conversions can be inverted depending on what you need. You do whatever you have to do to cancel. If we had started with ounces here, we would have needed to put the 16 ounces on the bottom to cancel the units. In this case, because we started with seconds, the 60 seconds has to go on the bottom and the minute has to go on the top to cancel the units. This is a really good way to make sure you don't make any mistakes in a conversion problem. If your units don't cancel, if you end up with seconds on the top in both steps, you know you've got something done incorrectly. And of course, this ends up being 62.3 minutes. Now, conversion problems can have more than one step. In fact, I can promise you on your quizzes and exams, you will not have any one-step conversion problems. They are going to have more than one step. I don't want to insult you by making the problems too easy. So, how many ounces are there in 1.55 tons? First thing we realize is, oops, I don't know how many ounces there are in a ton. I don't even know that. But that's okay. All I have to do is figure out how I can connect those two together. And to do that, I want to come up with something called a unit plan. A unit plan is sort of like a road map that takes you from your starting point to your ending point. So the first thing you have to identify in your unit plan is your starting unit. And in this case, it's the tons because that's the thing we know. Then we have to figure out what our target is. Where do we want to end up? Well, we want to end up with ounces. Since we don't know the conversion directly between those two, we want to find out how could we connect them. Do they have someone that they both know, some unit that's common to each of them? And of course, that's going to be the pound. We know how many pounds there are in a ton. We know how many ounces there are in a pound. So by going through two steps, we can get from our starting point to our ending point. So we'll begin with our 1.55 tons, and then the unit plan says, oh, change that into pounds. The rule is very simple. Whatever unit you're going to always goes on the top. The unit you're coming from always goes on the bottom, and in that way, the units cancel. The same thing will be true in this second step, where we want to get to ounces, so it goes on the top. We're coming from pounds, it goes on the bottom, and those units cancel. And then we're left with ounces, which is our desired unit, and there's our answer. Okay. How many miles would equal 583,000 inches? That's a lot of inches. Again, let's set up that unit plan. So we'll begin with our known, which is inches, and we want to get to miles on the other side. So how do we get from inches to miles? Well, we can go through feet, because we know how many inches there are in a foot, and we know how many feet there are in a mile. So we'll begin with our 583,000 inches, and again, as usual, we'll put the unit on the top we want to get to. So even though you're used to writing it as 12 inches per foot, we're going to flip it upside down here because we need those inches to cancel out. Same thing is true with our next conversion. We're going to put the feet on the bottom so the feet cancel out, and that tells us that we have a distance of 9.2 miles. Now, because most of the world uses the metric system, but here in America we're still holding out with the English system, it's important for us to be able to relate those two systems. I know on my trips to Canada, if you go to Canada, you're going to find, for example, that gasoline is sold by the liter rather than the gallon. And if you're looking at the price in Canadian dollars per liter, it's helpful to be able to get an idea of what that costs in US dollars per gallon. If you're driving down the road, you'll see all the speed limit signs are in kilometers. They're not in miles. So it's very useful to be able to relate those two. Now, there are hundreds of different conversions between all the various metric and English units, and that could get very complicated, but we're going to make it simpler. Suppose we had a group of Russians that only spoke Russian, and a group of Americans that only spoke English. Would everybody have to be bilingual? No. Let's suppose we just taught this guy here to speak both English and Russian. Anybody in the Russian group then that needed to communicate with the Americans could simply pass the message through their buddy here, and he could then translate it into English. So we don't really need to have hundreds of different conversions, we just need a few. For each different kind of measurement, whether it's length or mass or volume, we need one guy who's bilingual, one that can speak to the other group. In the length category, this is the one that we commonly use. It wouldn't have to be centimeters and inches, but somebody a long time ago thought that would be convenient, so that's what we use. If you needed to get, say, from meters to inches, you could go from meters. The meter could talk to the centimeter, and the centimeter, of course, could communicate with the inch. If you wanted to go from meters all the way, say, to feet, the meter could speak to the centimeter and say, centimeter, could you pass a message on to the English units for me? And the centimeter says, no problem, I'll just talk to my buddy the inch. And of course, the inch would then pass its message on to the foot. The same thing is true with weights and masses. And there's two that are commonly used, either 454 grams per pound or 2.2 pounds per kilogram. You don't need both of those. If you happen to know both, that's fine, but either one of those will be sufficient. When it comes to volumes, there are also two that are commonly used, either 946 milliliters per quart or 1.06 quarts per liter. So as long as you know this one and one of these two and one of these two, you'll be able to easily relate all the different units in the metric system and the English system. Let's go ahead and work through a few practice problems now. So first, let's figure out how many milliliters would be equal to 2.34 gallons. We'll begin, as always, with our unit plan. And since gallons is our known amount, that will have to be our starting point. And we're trying to find milliliters, so that will be our target. And since we don't know the conversion directly between the two, we have to find something they have in common, and that, of course, will be quarts. We'll begin then with our 2.34 gallons, and then we'll use our conversion between quarts and gallons, and we'll put quarts on the top so that the gallons will cancel. And to go from quarts to milliliters, of course, we'll put milliliters on the top so that the quarts will cancel. And we end up with 8,854.56 milliliters. Some of you are probably wondering, do we really need all those digits? And the answer is, it depends. So for now, we're not going to worry about rounding, but in a little while, I'm going to go over the rules for rounding, and there are rules. It deals with something called significant figures. But let's save that for now and just focus on setting up these unit plans and doing our conversion problems. In our next question, we want to figure out how many meters would be the 13-mile distance from Lodi to Stockton. So our unit plan, of course, will have to start with our known, which is miles, and we'll want to end with our unknown, which is meters. Now this is going to take a few more steps to connect. Miles is an English unit of length, meters is a metric unit, so we need to find our translator. And our translator, of course, is inches and centimeters. So if the mile wants to talk to the inch, it's going to have to go first through the foot. And of course, the foot can link to the mile. It can also link to inches. Once we get to inches, we can go ahead and use our translator, and we can go from the English system to the metric system. And then centimeters, of course, can connect with the meter. So we'll begin with our miles, and then putting feet on the top and miles on the bottom, we can cancel out the miles. And then our conversion of inches to feet, which lets us cancel out the feet. Then we plug in our centimeter to inch conversion, cancel out those inches, and then finally we go from centimeters to meters. The centimeters cancel out, and now we are left with meters. That is our desired unit, and we end up with 21,082 meters. For our next problem, we're making staples. So we have 1.65 tons of steel, and we know how much an individual staple weighs, and we'd like to figure out how many staples we can make. Again, our known here is the steel, so our unit plan will have to begin with our tons of steel. And we're trying to find the number of staples, so that's going to have to be our target. From tons, we can go to pounds because we're trying to get to milligrams, and so we need to make it to the metric system. And of course, the unit that can talk to the metric system in terms of weight is the pound. So once we get to pounds, we can make that jump over to grams using our translator. And then from grams, of course, we can go to milligrams, and then using our mass of each staple, we can go from milligrams to staples. So we'll start out with our tons, and then we'll convert tons to pounds, and make sure we cancel out the tons. Then we can go from pounds to grams using our metric English conversion that we mentioned a little bit earlier, and that'll cancel out the pounds. Then from grams to milligrams, we know that milli is 1,000 or 1,000th, so there's 1,000 milligrams in a gram. The grams cancels out. And finally, we have a conversion between staples and milligrams. We know that one staple is 35.4 milligrams. The milligrams cancel out, and that leaves us with a whopping 42,322,203 staples. Question 4 deals with blood sugar or blood glucose. So our average person has a little over 5 liters of blood, and we've measured their blood glucose level at 108 milligrams per deciliter. We would like to figure out how many grams of glucose are in their blood. So in our unit plan, we're going to start with liters. That's what we know, and we're going to end with grams. I'm going to move through these a little more rapidly now. You've seen me do several examples one step at a time. Now I'm going to sort of put it all together. So to get from liters to grams, this is clearly not one of our usual conversions. The conversions that we've been learning always either involve 2 masses, 2 volumes, or 2 lengths. When you're going between 2 different kinds of measurements, like a volume and a mass, you know you're going to need some extra conversions, and that's why I provide them in the problem. So many of these questions, as you get on a quiz or exam or on your worksheets, if you need additional conversions other than that short list in your objectives that I asked you to learn, I will simply provide them. So if we look at the blood glucose level, it is in milligrams. So if we could get to that point, we could easily figure out grams. However, our glucose level is measured not in liters, but in deciliters. So our logical first step would be get liters of blood into deciliters so that we could then connect with our blood sugar. So we'll go from liters to deciliters, and then we can go from deciliters to milligrams using our blood glucose level, and then of course milligrams to grams. Like liters to deciliters, that's simply a metric to metric conversion in each case. So we begin with our 5.1 liters, and we change that to deciliters. Remember, deci, like decade, tells us there are 10. Our liters cancel out. Then we can go from deciliters to milligrams using our blood glucose level, and our deciliters cancel out. And then finally, it's simple to change milligrams to grams because we know there are 1,000 milligrams in a gram. Our milligrams cancel, and we end up with 5.508 grams of glucose. Now let's do a problem involving some other units. We'll put in some units of time in this case. So we have the speed of sound in meters per second, and we'd like to know how long would it take a sound wave to travel 100 yards, the length of a football field. So our unit plan is going to have to start with yards. That is our given, and we want to know how long it would take, which means we need to get to seconds. So essentially, since the speed of sound is in meters and our distance is in yards, we just have to change yards to meters. So this is another English to metric length problem. For the yard to get to the metric system, it has to go through its go-to guy, the inch. So if we change yards into feet, we can then go from feet to inches, and now we're ready to make that jump into the metric system. The inch, of course, can talk to the centimeter, and then the centimeter can connect with the meter. Once we get to meters, we can go ahead and use the speed of sound to convert our final answer into seconds. The setup for the problem then, we're going to begin with our 100 yards, and we'll change that into feet and then feet to inches. Now we can use our translator pair here to go from inches to centimeters. Centimeters, of course, can easily be related to meters using our metric prefix centi, and then we can use the speed of sound to convert our final answer into seconds. If we take a look, all of the units cancel up and down, and that leaves seconds as the only unit standing at the end, and it comes out to be 0.27459 seconds. That's just a little over a quarter of a second. So sound travels pretty fast. All right, back to a human question again. This time we want to figure out how long a person can live off their stored body fat. Lots of animals store fat to take them through lean times, and people are no different. So let's suppose that this person has 11 kilograms of body fat, and we know that each gram of fat contains 9 calories. When you burn a gram of fat, it produces 9 calories of energy. So if a person needs 2,100 calories each day to survive, how many days will they be able to live off of the energy they get from their fat? So in our unit plan, our starting point, of course, will be the kilograms of body fat, and we want to find out how many days they can survive. Well, we can see here that days is related to calories, and calories is related to grams of fat. So if we could get kilograms converted into grams of fat, we would now be able to link it up with this conversion of 9 calories per gram. And once we get to calories, we can use our second conversion to go from calories to days. So we'll begin with our 11 kilograms, and then using our metric conversions, we'll change that into grams. Now we can get from grams to calories because we know that there are 9 calories in each gram of fat. And then finally, every day the person needs 2,100 calories. Again, our units cancel. The kilograms, the grams, and the calories all cancel out diagonally, leaving us days, and it comes out to be, surprisingly, a little over 47 days. So in theory, a person could survive an awfully long time without food as long as they have water. All right, one last practice problem here before we move on. The human heart beats around 65 beats a minute. Some people faster, some slower. And the average heartbeat pumps about 75 milliliters of blood. So given that, how many gallons of blood does your heart pump each day? I think you'll be surprised. So our unit plan will have to begin with days, because that's the question. and we want to find out how many gallons of blood can be pumped. Well, our heart rate is not based on days, it's based on minutes, 65 beats a minute. So the first thing we'll need to do is get days into minutes, and that's pretty simple. Just we'll go from days to hours, and then from hours to minutes. Now we have a conversion here of 65 beats per minute, so we can relate minutes to beats, and then we have a second conversion that relates the number of beats to milliliters. So we can use that conversion to go from beats to milliliters. And then to get to gallons, of course, we'll need to have a go-between, which is the quart. We have a milliliter to quart conversion. We also have a quart to gallon conversion. So this was a pretty long problem here. 1, 2, 3, 4, 5, 6 steps. That's about as long as you're going to see, at least from me. So we'll start with our 1 day. We've got 24 hours per day, of course, and 60 minutes in an hour. Then we can use our heart rate to figure out how many beats, and we can use the pumping volume to figure out how many milliliters the heart can pump. And then we'll simply change milliliters into quarts and quarts into gallons using the conversions that we've already learned. Again, we'll check our work, and it looks like days, hours, minutes, beats, milliliters, and quarts. All those units cancel out exactly as they should, and that leaves us with gallons, and surprisingly 1,855 gallons. I figured out that my heart could probably fill my entire swimming pool in about a week. That's actually pretty amazing. When we did our activity on the scientific method right at the beginning of the class, we talked about density and how density was responsible for some of the cans sinking and some floating. Of course, I know all of you have learned about density. You've done that probably in junior high and high school basic science classes, but just as a refresher, density is simply the mass of an object divided by its volume. We'll also be doing an experiment this week all about measurement and density, so you're going to get lots of practice working with this. Now, when you learn about density in junior high or high school, you normally solve the problems algebraically. So we can write the equation D equals m over v. That's one way of writing the density equation. So if you know the mass and the volume of something, you can calculate its density. But what if you wanted to find one of the other variables, the mass or the volume? What teachers normally have you do is simply rearrange the equation. If we wanted to find the mass, we could simply solve it by determining that mass equals density times volume. If we wanted to find the volume, that's mass divided by density. That's one way to approach these problems. But there is an easier way, especially when we're working conversion problems. Consider, for example, the density of aluminum. It's 2.7 grams per milliliter. Now, if you look at that density, it ought to remind you of something. It should look really familiar. What it should look like, of course, is a conversion. We've been dealing with conversions all through this discussion, and we remember the conversions are fractions. They have two different units in them, and they're equal to 1. Well, 1 milliliter of aluminum weighs 2.7 grams. The fact is, density is simply just another conversion. So we don't need to treat density as something special or unique that has to be dealt with by itself. It's simply going to be another conversion we will add to our arsenal. For example, then, let's suppose that we had 346 grams of aluminum and we wanted to figure out what the volume of that would be in milliliters. Let's set this up like a conversion problem. We'll begin with our known, which is grams, and we would like to convert that into milliliters. So gosh, if we had a conversion that related grams and milliliters, there'd be no problem, and of course we do. So we can simply plug in the density. Now you'll notice, as we talked about earlier, conversions can be flipped upside down. I had to invert the density here in order for the grams to cancel. I wanted grams to cancel. I wanted to be left with milliliters. So the grams cancel out, and I end up with approximately 128 milliliters. So we didn't need to use any algebra to figure this out. We simply used the density as a conversion. Let's try a problem now where we combine density with other conversions. We know the density of mercury is 13.6 grams per milliliter. It's a very dense liquid. And we'd like to figure out how many pounds there would be in 1.35 gallons of mercury. Just for comparison, that much milk or water would weigh about 11 pounds. So see how it compares once we finish this problem. For our unit plan then, we will have to begin with what we know, which is gallons, and we're trying to figure out how many pounds of mercury we would have. Again, this is a problem where we have two different kinds of unit. We have a volume here, and we have a weight over here. When you have a weight and a volume, or a mass and a volume, it's very often a density problem, since density relates mass and volume. If you see those two types of units, and you notice there's a density given in the problem, that's a pretty good giveaway that it's going to be a density calculation. Now, densities aren't in gallons, they are in milliliters. We'll want to get gallons turned into milliliters, and therefore we will have to go through the quart and then on to the milliliter, because the quart can connect with both of those. Once we get to milliliters, we can now make the jump over to grams, and then of course it's relatively easy to go from grams to pounds. So we have simply used density as one of the conversions in this series. We'll start out then with our 1.35 gallons and change that into quarts. And we put the quarts on the top so that the gallons will cancel. From there we'll go to milliliters, and again milliliters on the top so the quarts cancel. Then, using the density, we can go from milliliters to grams. This time, we put the mass on the top, unlike our aluminum example, because we want the milliliters to cancel. And then finally, we can just change our grams into pounds using our conversion we learned earlier. And it comes out to be 153 pounds. I think most of us, myself for sure, would have a lot of problems lifting up 1 1/3 gallons of mercury. It would be incredibly heavy. I mentioned a little while ago that we would talk about the concept of rounding. How do you know when to round off an answer? It turns out that rounding is an important concept because the number of digits that you leave in your final answer tells people how accurate the reading is. I'm going to have you guys watch a video now by Melissa Maribel, who does a lot of chemistry videos on YouTube. You'll notice that occasionally if I find a really good video on YouTube, rather than reinvent the wheel, I'll simply incorporate that. So let's take a break here. We'll watch that video, and then we'll come back and we'll work through some examples where we use significant figures to round some of the answers for the problems we worked out earlier.
So what are significant figures? Significant figures, or sig figs, are the digits within a number that help determine how accurate a data value or measurement is. And of course, there are rules. Rule number 1, all numbers that are not 0 are significant. Looking at this first example, every single one of these digits is significant because they are non-zero numbers. Rule number 2, any zeros that are in the middle of non-zero numbers are significant. These two zeros are in the middle of 5 and 8. 5 and 8 are two non-zero numbers, so every single digit counts as significant. Rule number 3, zeros after the decimal are significant. These 3 zeros are after that decimal place, so every single one of these digits is significant. Rule number 4, Any zeros and coefficients in scientific notation are significant. Notice we have our scientific notation with something being multiplied by 10 to some sort of power. This 8 and this 0 are significant. Okay, grab a pen, write this down. Do you need a pen? Okay, you can borrow mine. All right, now that you're ready, write this down. Rule number 5, any leading or beginning zeros are not, I repeat, not significant. Looking here, these 3 are leading or beginning zeros. They do not count as significant. Only this 4 counts, so there's only one sig fig. Rule number 6, any zeros in a large number without a decimal are not significant. These 3 zeros are within a large number without a decimal, so they do not count as significant. Only the 4 does. There's only one sig fig. But wait, there's more. When adding and subtracting numbers, you look for the least amount of decimal places. For this first example, your first step is to line up all the decimal places. Notice how 5004, there is no decimal. However, where the decimal would be after this 4 in the ones place. So since we're looking for the least amount of decimal places, that 5004 doesn't have a decimal place, so we will round to the ones place. Remember, when rounding to the ones place or rounding any number, you look at the one right next to it to the right, and if it is 5 or more, you round up. Your final answer will be rounded up to 5,488. We have 4 sig figs. Moving on to multiplication and division. When multiplying and dividing, you look for the least amount of sig figs. Your first step is to figure out how many sig figs there are within each number. Notice that there are 3 sig figs in this first number and 6 sig figs in the second. So we will round to 3 sig figs. After multiplying, you then want to go ahead and stop at this 0. So you remove that decimal place, and there really only are 3 sig figs. Because of that last rule, this 0 does not count. There is no decimal place. It's within a large number. Only these 3 count as sig figs. It's time to check yourself. Go ahead and try these practice problems. All right, let's recap what we just learned. Significant figures are the digits within a number that help determine accuracy. The 2 rules that you gotta know. Any leading or beginning zeros do not count as significant. Any zeros in a large number without a decimal are not significant. When adding and subtracting numbers, you look for the least amount of decimal places. When multiplying and dividing, you look for the least amount of sig figs. If you feel like you need some more practice, check the description box below. There's a link with practice problems and step-by-step answers. And make sure you like this video if you learned something. And subscribe if you want to see more videos just like this one. Remember, guys, I am here to show you how to pass chemistry. So leave a comment below letting me know what you need help with. And I'll see you next time.
Now let's go ahead and review what you learned in that video clip and do some examples of significant figures. First of all, there are 2 kinds of conversions that we'll be using, and they have a different number of significant figures. The first of those are called measured conversions, and of course they're called measured conversions because we have to measure them. It's something that we had to actually go out and use some kind of device to measure their value. For example, when the French came up with the metric system and they invented the gram as a unit of mass, they had to figure out how the gram related to the pound. So probably someone weighed something in pounds, they weighed the same thing in grams, and they figured out what the relationship was between the two, and they made their conversion. Now, of course, when you measure something, you can't measure it exactly. 454 grams means that we're within a gram. So as we've talked about earlier, the measure of 454 could be 1 gram higher or 1 gram lower. This particular conversion has 3 significant figures. Same thing is true with our milliliters to quarts. Somebody back there in the 1700s had to figure out the relationship between the two, and we know that to within a milliliter. So again, we have 1, 2, 3 significant figures. The density of aluminum, 2.7 grams per milliliter. This one had to be measured, and this one's only been measured to 2 significant figures, so it's not as accurate. If we add another digit there, every time we add another digit, it makes it 10 times more accurate. From one of our earlier problems we did about the blood glucose, that 108 milligrams per deciliter, that was measured to 3 significant figures as well, because someone had to actually take a sample of blood and measure the amount of glucose. So we can't measure things exactly. We can only measure them approximately, depending on how good our measuring devices are. Now there's another kind of conversion which we call defined conversions, because they're definitions. Someone simply said, let this be the conversion. For example, are there approximately 100 cents in a dollar, or are there exactly 100 cents in a dollar? And of course, it's exactly. If you go to the bank and you give them 98 cents, they're not going to give you $1, and you wouldn't be very happy if you handed them $1 and they only gave you 98 cents. When the founding fathers came up with a monetary system for our new country, they decided to use the dollar as our basic unit, and of course back then $1 was a lot of money. So they decided, well, let's divide that dollar into 100 equal parts, and we'll call them cents. And you may have never thought about that, but the reason it's called a cent is because it's basically a centy dollar. It's 100th of a dollar. So this conversion has infinite significant figures because it's defined that there are exactly 100 cents in a dollar. So when you're doing rounding, this conversion would not affect your rounding because it's infinitely accurate. Whenever you have 2 units from within the same system, like these are both metric units, that's a definition. When the French devised the metric system, they said, oh, let's divide the liter into 1,000 equal parts, and we'll call those milliliters. And so by definition, there are exactly 1,000 milliliters in a liter. If your units are both in the English system, we can assume that they are definitions. Somebody at some point, hundreds of years ago, came up with this measurement of the foot, and the foot was great, but sometimes you wanted to measure smaller things. They said, well, let's come up with a smaller unit. We'll call it the inch. And they simply said, let's make the inch exactly 1/12 of a foot. So for whatever reason, they decided there should be 12 inches in a foot, and there are exactly 12 inches in a foot. Our units of time are the same way. The hour is divided into exactly 60 minutes by definition. So anytime you have a defined conversion in a problem, that conversion is exact, and therefore it does not affect your rounding. Only measured conversions. When you measure something, it can't be exact, and those will affect our rounding. Let's take a look at a couple of the conversion problems we did earlier, and now figure out how we should actually have rounded our answers. So this is one of the ones we did before. We converted gallons into milliliters. The rule for rounding, as you saw in the earlier video, is we measure the number of significant figures in each of the numbers we use to calculate our answer, and our answer can be no better than the weakest of our numbers that we use to calculate it. It's the old saying that the chain breaks when the weakest link breaks. So if you have 2 numbers and one has 2 significant figures and the other has 5, your answer can only have 2. A bad number and a good number are going to make a bad number. So you can only be as good as the least accurate value you have. So 2.34 gallons, we've got 1, 2, 3 digits in there, we have 3 significant figures. 4 quarts per gallon, those are both English units of measurement, which means that's a definition, and that will have infinite significant figures. And then the milliliters per quart, again, that's something that we had to measure back there in the 1700s, so 1, 2, 3 digits. It also has 3 significant figures. And that means that our final answer can only have 3. The way I've written it now, it's got 6 significant figures. We're telling people that we know this to the nearest hundredth of a milliliter. Well, that's not true. There's no way with this only relatively accurate measurement in gallons that we could know our milliliters that accurately. So we want to round this off to 3 significant figures, which means we can keep the 8, we can keep the second 8, and then we'll take our third digit and we'll round it off to the nearest whole number. And since we're followed by a 4, that means we would round it down to the 5, and we would get 885 milliliters, and that has the correct number of significant figures. Another problem we did was calculating the number of days a person could survive on their body fat. So let's go through each of these values and figure out how many significant figures they have. If you remember, a 0 after a decimal point like this is significant. If we left that 0 off, it would read 11 kilograms, and that would mean somewhere between 10 and 12, not very accurate. By adding the 0, we're telling people it's measured to the nearest tenth of a kilogram. Now it's somewhere between 10.9 and 11.1. So this one has 3 significant figures. The gram and kilogram conversion, of course, they're both metric conversions, which means this one has infinite significant figures. The calories in a gram of fat, of course, someone had to measure that. We're going to be doing an experiment later on calorimetry, where we learn how to measure that type of thing. This one only has 2 significant figures, so it's not as accurate. And finally, the number of calories per day. If you remember from the video, when you have a large number like this, the zeros at the end aren't actually significant. So only the 2 and the 1 are significant, which means, again, we only have 2 significant figures. So 2 is the smallest number of significant figures that we have, which means we can only have 2 in our final answer. So we can keep the 4, and we'll need to round the 7, our final significant figure, to the nearest whole number. And again, since it's followed by a 1, we would round it down, and we'll end up with simply 47 days. So that essentially tells people it's somewhere between 46 days and 48 days. It's 47 plus or minus a day. In our first experiment this week, we're going to be doing measurement in density, and we're going to be measuring volumes of liquids in various pieces of glassware. Just as an example, and I'll be talking about this in the pre-lab video as well, but let's look at an example of how you would measure this volume and how many significant figures you would actually be able to have. When we measure the volume of a liquid in a piece of glassware in the lab, we always measure it at the bottom of this thing called a meniscus. So this arrow points right to the bottom. That's where we're going to measure the value. If we take a look at this burette, we can see that the volume is definitely between 12 and 13. So clearly the volume is 12 point something milliliters. But we can do better than that. We can be more accurate than just 12 milliliters. Each of these increments, you can see that there are 10 of them between 12 and 13, which means each one is a tenth of a milliliter. So we're at 12.1, 2, 3, 4, 5. Clearly, our water level is somewhere between 12.5 and 12.6, so we can also be very sure that our next digit is a 5. Can we go any further? Well, we can't be absolutely certain of what our next number is, but we can make a ballpark estimate. It looks like it's somewhere near the middle. It's clearly not 12.51, it's not 12.59, it's somewhere in the middle. To my eye, it looks like it's just a little bit shy of halfway between 12.5 and 12.6, so I'm going to call it 12.54. You might look at it and think, oh no, I think that's 12.55. Well, we're both right, because remember, the last digit in a measurement is always assumed to be inexact. It could be one digit higher or lower. So if we reported this as 12.54, what we're telling people is it's somewhere between 12.53 and 12.55. You always want to record your measurements or report them as accurately as possible. Now, I wouldn't want to write down 12.54396 milliliters because I have no idea what's beyond the hundredths place. The rule of thumb for measurements is whatever the smallest increment is in your measuring device, you can go 1 decimal place smaller. Our measuring device here, this burette, is marked off to the nearest tenth of a milliliter, which means we can estimate it to the nearest hundredth. If your measuring device was only to the nearest milliliter, then you could go estimate it to the nearest tenth of a milliliter. And we'll talk more about that in this week's lab experiment. The last thing I want to say about rounding in significant figures is some good news, and that is I'm not actually going to grade you on whether you round your answers off to the correct number of significant figures. If you go on to general chemistry and you take, say, Chem 1A, they will expect you to round things accurately. They want you to not only get the right answer out of your calculator, but to be able to round your answer to the appropriate number of significant figures. So for those of you that are going on, you might want to pay attention to that as you're working through the problems. But just keep in mind, I'm not actually going to dock you. If you had simply called this 12.5, I would have let that go. That would have been okay. So when you're using your calculator and you get a lot of digits in your answer, if you leave them there, that's all right. If you want to try to round them, that's perfectly fine as well.